Great. So I'm going to talk about this project Succinct that we started when I started at Berkeley. And the high-level goal of the project is to enable certain kind of queries directly on compressed data. So what I want to talk about today is why do we want to do this? How do we do this? And what does it look like when we do this? So let me start with why. Okay. And the main idea, the main application that we wanted to target was this distributed data stores that a lot of cloud services use today to build different kind of services. And we already know a large number of distributed data stores, starting with simple DHTs to more complex Cassandra, MongoDB, and towards the end, more database style, Vertica and SAP HANA. Right. So these data stores differ very, very much in details and the kind of functionalities they provide. But just to set the terminology for the talk, let me start with what I'm going to use the three main words: records, primary key, and secondary keys during the entire talk. So these data stores typically store the data as collection of records. So let's consider this very simple table where I have a few users and what those users' position is at UC Berkeley, who their boss are, and how do they describe their boss. So let's say the description or the information about each user, I'm going to call it a single record. And each of this record can be accessed or can be written or can be accessed using what I'm going to call primary key. Okay, so the application is going to specify one specific key, one specific column, which I'm going to call primary key. And all other keys are going to be the secondary keys in this table. Okay, just the terminology thing. Okay, so let's look at queries in data stores. Okay. I'm going to differentiate between two kinds of queries. The first query is going to be on primary keys. And this is something that we have already seen with key value stores and NoSQL stores. And the three main queries that we know of is random access, where you give a primary key and you want to access a record using a primary key. And you want to append new records using put, and sometimes you want to delete the records too. It turns out that over the last few years, we have made these queries extremely efficient. If you look at some of Dave Anderson's work, for example, you can get hundreds of thousands of operations per second using a single server. So very, very efficient. On the other hand, we have these queries on secondary keys that we have not focused so much on for some reason or other. For example, you may ask a very simple query, give me the list of all postdocs at UC Berkeley, right? Typically, if you look at these data stores, Cassandra, MongoDB, or Elasticsearch, these queries on secondary keys will be executed via two main techniques. Okay. The first technique is data scans, and columnar stores like Vertica or SAP HANA execute these queries search via data scans. The second technique is so-called indexes. Okay. Sometimes I'm going to call them secondary indexes for not so interesting reasons, but these are indexes. And if you look at Cassandra and MongoDB, they generally construct indexes on secondary keys, and then you can execute queries using these indexes. It turns out that these queries on secondary keys are either very slow for the case of data scans or have very high storage overhead. So I'm going to go deeper into why this is true. Okay. But let me take a step back and forget everything that I told you about primary keys, secondary keys. And let's consider a simpler problem to understand this slow versus high storage overhead problem. So I'm going to take a step back, get out of structured data, and get into a very simple flat file interface. Okay? So there are no columns, there are no records, there are nothing, just a flat file. And I'm going to talk about queries on flat files for now. It turns out that these queries on flat files are actually very, very powerful. Okay? They already allow queries on semi-structured data, and I'm going to discuss that later on. So let's start with this simple query search, right? What I have is an input file. I cannot move around. Okay. I have is a very simple flat file, different objects of different colors, and what I want to execute is a very simple search, find all the objects that are green in color. So as I said, the first option today is to execute using data scans, and you will take your input file, store it as much as you can in the faster storage, and then starting from the first object, you will start scanning. It takes some time, but the scan completes and you output the results. Now, since you're storing only the input file, your memory footprint is obviously very small, but scanning the data takes some time, so you can incur very high latency. Okay. Okay. The second option is, as I said, indexes. You take your input file, you pre-process it, and you construct some sort of index that is very aligned to the kind of queries you are going to execute. Now, when a query comes in, what you're going to do is look at the corresponding entry in your index and simply output it. Okay. So what's the nice thing? The nice thing is that these indexes are extremely fast, extremely good, right? The bad thing is that you have to store the indexes on top of your data, right? Because you also want to store your data to get random access. You have to store these indexes in addition to your data, and sometimes these indexes can be much, much larger than your input data size, depending on the queries you want to execute. So I'm going to say that they have high storage overhead, but very low latency. Okay. So you see, in data scans, we have low storage, high latency, while in indexes, we have high storage and low latency. So why is this a problem? Let's see what happens when I try to plot this curve. On the x-axis, I'm going to increase my input size from left to right. And on the y-axis, I'm trying to understand what would the latency look like for a system that has some fixed amount of faster storage. Okay, so think of SSDs or main memory. So if I look at data scans, the first part of the data scans, you are going to scan in faster storage, as much data as you can fit. And it's slow, but it's not too bad. Then you go to slower storage, and your curve changes, your overhead starts increasing. Indexes, on the other hand, are extremely good when you can store indexes in faster storage. But as I said, indexes are very large in memory footprint, and hence they go out of faster storage very quickly. And you end up indexes in slower storage, which have very high overhead, very high latency. And this is really the penalty you are paying for having such high memory footprint for indexes. Okay. So the question is, can we avoid paying this penalty? Can we somehow push more data into memory? And that is how we started this project, Succinct, where we literally wanted to push more data into memory precisely for this reason. So let's see what Succinct does. Okay, so Succinct does two things. First is it pushes more data in faster storage. How does it do that? We are going to ensure that our storage is never, ever going to be more than the input data size. Okay. Now you still want to answer queries like search queries. So imagine just for a second that if I don't even give you enough space to store the input data, how would you execute a search query? Right. So what Succinct is going to do is it's going to compress your input data in some manner that I'm going to try to describe later. And we are going to execute queries directly on this compressed representation. Okay. We are not going to do any data scans. We are not going to do any data decompression. Execute queries directly on compressed data. And to achieve these two goals, we are going to target on read-heavy, append-only workloads. We are not going to do in-place updates. We are not going to look at write-heavy workloads. And we are not going to worry about fault tolerance and data consistency, at least in this paper. Okay. So let's see what Succinct would do for the same example that I discussed earlier about data scans and indexes. Succinct would take your input file, it would pre-process it, and it would construct a suite of data structures. What I really want to emphasize here is that Succinct does not store the input data. It just stores this compressed representation and nothing else. Okay? And then it's going to execute the queries directly on this compressed representation. So we have very low storage. We are not even storing the input data, so it's even less than data scans. And the hope is that we can push this data in faster storage and hence get very good latency. So what makes Succinct unique is that we are not storing any additional indexes, right? As I said, all the query responses for a particular set of queries that I'm going to define later, these query responses are going to be embedded within the compressed representation. We are not going to do data scans, so we're essentially providing the functionality of indexes without storing any indexes. And the only time we do decompression is when you actually want to access the data, and I highly suggest you not to do that. Okay, so let's get back to this graph and see where Succinct fits. So essentially, this is where Succinct fits. If you think about it, in comparison to data scans, we avoid data scans and hence get good latency. In comparison to indexes, we avoid queries of slower storage and hence get gains. Okay. So to the most important slide, the question is, what do we lose? Okay, hopefully you're impressed by now. So I have to tell you, what do we lose? No secondary indexes, no scans, no decompression. You must be crazy. No, actually not. We lose quite a lot. Okay. To achieve these properties, we made very specific trade-offs in Succinct. The first trade-off is the pre-processing is terrible. Okay. We take a lot of data and pre-process it for a lot of time, roughly 4 gigabyte per core hour. We use a slightly extra CPU when you actually want to decompress the data or actually want to do data access. So in comparison to storing the input data itself, we do extra CPU access. You don't want to read a lot of data in Succinct. You really want to do random access of small, few hundreds of kilobytes, because the sequential scan throughput is not very good. So you don't want to use Succinct for Hadoop-like queries. And we don't do in-place updates, as I talked about earlier. Okay, so now let me tell you how. Okay, and I'm already running out of time. So Succinct builds upon a lot of theory work. There's something called Burroughs-Wheeler transform, which has been used very extensively in theoretical computer science to build techniques where you can execute queries on compressed data. There's another side of work which is called compressed suffix arrays, and Succinct ends up using this. But while we were building the system, we ended up doing some innovation, both in terms of data structures and in terms of query algorithms. So I'm not going to have enough time to talk about the entire algorithms. I'm going to try to give you some intuition and refer you to the paper, which itself refers to the tech report. So you're welcome to go to the tech report and read it. So let me now tell you about 3 arrays. I'm going to define 3 arrays. The entire magic in Succinct is about these 3 arrays. The first array is something that we are going to call array of suffixes. Suppose I have this input file. The first line in the file is just showing the index into the file, and happy puppy is my file. What Succinct does is, it first constructs the set of suffixes in your input file. Okay. Essentially, the first suffix is the entire suffix, takes the 1, and it constructs the entire set of suffixes. Okay. The second thing it does is it sorts these suffixes lexicographically. Okay. Okay, so this sorted set of suffixes is something that I'm going to call array of suffixes. The second important data structure, which you might be more familiar with, is something called suffix arrays. It's very similar to suffix trees, but less memory intensive. So we have this sorted set of suffixes. Go to each suffix and just store its location in the input file where the suffix starts. So for example, for the first one, it starts at location 1, you write down this, and then the second one starts at location 0, and so on. Okay, this is something I'm going to call EOS to input. So we have these 2 arrays. The first one is array of suffixes, which is just sorted set of suffixes, and the second one is EOS to input. Now suppose I want to execute search, right? How would I execute search? It's rather simple to see that you can actually do arbitrary substring search. It doesn't have to be any word aligned or anything. You can do arbitrary substring search by binary search on this array. Okay. And once you have searched over AOS using binary search, you can get corresponding locations in the input file using input to AOS. Does that make sense? Okay, good. So we can do arbitrary succinct search. What's the problem? The problem is that I'm joking. You, you cannot store these two arrays, right? The first one is already requires n squared bits, and your input file is n bits. So you can't store this array. The second one is storing pointers into the input file. So it requires log n bits per entry. So these two arrays are massive. So we are going to adapt some techniques from suffix tree literature, where they have shown how to avoid storing the entire set of suffixes and still get the functionality of AOS. The main idea is as follows, okay? And I apologize for these next two slides. They are going to be slightly extensive. The main idea is as follows. You start with the main suffix, so happy puppy, over here, the second suffix, and see it starts at location 0. So what you're going to do is store a pointer to the suffix after removing the first character. Okay? So now notice that I don't have to, out of happy puppy, all I have to store is h and this pointer, because then I can construct the entire suffix by following this pointer. And I can repeat that and store another pointer from 1 to 2 and forget about storing anything other than the first character. Essentially, I can keep constructing these pointers, right? And all I have to do now is just store the first colored line, that is the set of characters in the input file. So this is what we are going to call a next char index, which is nothing but index of suffix after removing the first character. Okay, good. So suppose I store next char index. Suppose I can store that, and I'm still joking. Suppose we can store that. We can get rid of this n squared bits of space. Then another observation is that since these suffixes were sorted, I don't even need to store one character per file value. I just need to store all unique characters in the input file, and I'm done. So I've taken care of the first problem. The second problem is much more tricky to take care of. And the problem is that there is literally no redundancy in AOS2 input. It's a crazy array. Okay. So how do we do that? To take care of this array, what we do is we try to see another structure in this next char index. We are going to interpret this next char index array in a different way. So the first interpretation was you take your suffix, you remove the first character, and you store the pointer. But if you think about it, input to AOS is storing the locations in the input file for the suffixes. So if I remove the first character, I'm actually storing where is the next larger value stored for input to AOS. Okay, so if you look at 0, for example, this pointer is telling you where is 1 stored in the input file, because it is the location of the suffix after removing the first character. Okay, good. So for 1, the pointer will say where 2 is stored. So what I can do is, even though there is no redundancy in AOS2 input, what I can do is I can sample this array, okay, store the sampled array, and the question then becomes is when I'm doing my binary search, how do I find unsampled values? The answer is you keep following the pointers in next char index until you find one of the sampled values. Okay? So for 0, if I want to find the second value, I'm going to follow the pointer, and I hit 1, which is sampled, and I can find such values. Okay, so I'm going to leave it there. Now the problem is that I still have to store next char index, which still requires log n bits per entry. And the beautiful observations that theorists made there is look at these values corresponding to all the characters that start with the same characters. These form increasing integer sequences. And increasing integer sequences are known to be compressible, okay, using, for example, run length encoding. So I'm not going to go into the proof, but it's not too hard. It's like 3 lines of proof. It's intuitively described in the paper. So now we can store the sampled array. We can just store all the characters, unique characters in the input file, and this run length encoded data structure. We do something more than that. What we do is we take this next char index and transform it into a 2-dimensional array with the property that each row is a contiguous, not increasing, but contiguous sequence of integers and much, much more compressible. So that's something that you can look into the tech report. So let me quickly go into data model and API. The input is flat unstructured files for Succinct. We work with flat unstructured files. So if your original input is this, Succinct constructs these data structures. And now you can execute very powerful primitives like search. Okay, you can extract, which was random access, and you can do count queries, which will tell you the number of occurrences. You can append new data, and you can execute slightly stronger queries like range and wildcard queries. Okay, so I'm going to probably skip this slide. What I wanted to say here is that unstructured files are actually very powerful. We have already built a lot of abstractions on top of Succinct's unstructured file queries, including key value stores, queries on tables, and documents. So I had this. Basically, the idea is that you take your semi-structured data, assign each column a particular delimiter, and then transform it into a flat file with delimiters appended to the values, and then you search by simply changing the queries. You can now execute queries on semi-structured data. So the last slide before evaluation is Succinct handles appends using a multi-store architecture, which is very similar to Dave's SILT work from SSP11. And the main challenge there is to support the queries efficiently. You are welcome to look for details in the paper. The high-level idea is that we have this log store where the data comes in as written. Since queries in log store are executed via scans, we cannot have very large log store size, but we also want to accumulate a lot of data before compression. So we use an intermediate store called suffix store, and the rest of the data is stored in Succinct store, which is memory optimized. Okay. The system has a coordinator which does two very simple tasks right now. The first task is cluster management, which is just like any other coordinator. The second task, which is slightly more interesting, is the data management, where you have to maintain a certain set of pointers to quickly locate the data. Okay. As the data moves around from log store to suffix store and suffix store to Succinct store, these pointers are very useful and are pushed to the servers by the master. I'm going to talk about one important thing in Succinct, which is potentially a killer aspect, but we found it very interesting. Each of these machines, they have a query handler interface. Clients can connect to any of the query handlers and execute queries. One interesting thing in Succinct is whenever you have a query on primary key, we always go to a single machine, just like any other system. But if you have a query on secondary key, we end up going to all the machines unless you have a columnar store kind of query. So this is partition aggregate, standard partition aggregate kind of query. Okay, so I'm going to quickly go into evaluation. We use two data sets. One is small KV, one is large KV. The main difference is the size of records for each of the data set. For small KV, we had 140 byte records, and for large KV, we had 1.3 kilobyte of records. We used Amazon EC2. All our experiments were run on Amazon EC2, 10 machines, 15 gigabyte RAM each. And we used a workload which was adapted from YCSB for queries on secondary attributes. We compared against 7 systems, but 4 of the systems are in the paper: MongoDB, Cassandra, Hyperdex, which actually supports search, and DBX, a good columnar store, which is actually surprisingly good. One thing that I want to mention here is that some of the numbers here, especially in terms of compression, actually depend on the data set. So the important thing is the trend, not the exact numbers. So let's see, what does the memory footprint look like? So for a small val and large val, the thick line you see here over 150 gigabytes is the entire memory in the cluster, the main memory RAM. So what Succinct does, as we talked about earlier, is that it actually pushes more data into main memory than the memory itself, right? So for example, for a small val, Succinct is able to push roughly 175 gigabytes of data on 150 gigabytes of RAM cluster, okay? While other systems generally give up on 17 to 20 gigabytes because of large indexes. So really the main takeaway here is that Succinct pushes a lot more data. Now before I go to the next slide, I want to set your expectations right. We are pushing more data into memory. So what we want to do in terms of results is show that our results for 190 gigabytes of data are same as other systems for 17 gigabytes, right? This is what I essentially wanted to show. So here's a throughput for queries on primary attributes, which is simply get queries and followed by 5% put queries, append queries. If you look at the first set of values, which is 17 gigabyte RAM, each of the system provides roughly 18 gigabytes. I don't think there's anything interesting about Succinct being better there. I think it's just that we don't have fault tolerance, we don't have other properties. So in terms of, for 17 gigabyte RAM, Succinct having better results is not interesting. What is interesting is that when we go from 17 gigabytes to 192 gigabytes, Succinct gets exactly and roughly similar throughput. Okay, there is no throughput degradation at all when we go from 17 gigabytes to 192 gigabytes, which is a fantastic thing about Succinct. And there are some theory results mentioned in the paper why this is true. So essentially, even for this 10x range of data sizes, we get exactly the same performance. Okay. So what other systems can provide with 17 gigabytes, we can provide with 192 gigabytes of data. More interestingly, when you look at search, so queries on secondary attributes, Succinct has a similar performance in terms of scalability. When we go from 17 gigabytes to 192 gigabytes, Succinct is still, it gives up a little bit compared to queries on primary attributes, but still maintains its throughput. What is interesting in this plot is I want you to think about MongoDB, which is the leftmost red curve for 17 gigabytes, and compare it with Succinct, which is the rightmost 192 gigabytes plot. What MongoDB provides for 17 gigabytes, Succinct provides with 192 gigabytes of data. This is what our original goal was. Okay, so we are doing queries on compressed data and providing you the functionality or performance of systems that put in much less data. So to summarize, Succinct pushes 10 to 11x more data in faster storage compared to popular open source systems. Succinct executes queries directly on compressed representation of the data. It avoids data scans and data decompression costs, and as a result, it's able to provide interactive queries on both primary and secondary keys for unstructured and semi-structured data. Thanks a lot. That's all I have.
Time for one question. That's not a question. Okay, well, I have a question. So as far as I could tell, you can't support delete or updates in place at this point. It's something you've been looking at?
So delete, we can support for semi-structured data. In-place updates is something that I think that's a fundamental limitation in some sort of compressed data structures and something we have not been looking at that much. But yeah, deletes is something we can support. In-place updates, the way Succinct executes in-place updates right now is a delete followed by an append. It is not the most efficient way to implement in-place updates, but I think this is sort of fundamental limitation of Succinct.
Okay, thank you very much.
I think there's a question there.
One more question.
Yeah, sorry, I was on my way to the microphone when you concluded there were no questions. I'm Edward Tremmel from Cornell, and I was thinking actually along the lines of Robert's question. So it seems like you've designed this system around append only. You don't really support in-place updates by design. How realistic is this of an assumption? What kind of workloads are you targeting that are just fundamentally append only, not going to care that you don't support in-place updates?
So yes, our main target was, if you think about key value stores, NoSQL stores, most of these would provide you the functionality with get, put, deletes, right? Put is kind of an append. Okay, they do not allow you to do in-place updates unless you want to do an append followed by a delete, which is what Succinct does that as well. We were not trying to support full-fledged SQL or database kind of queries, which is much stronger than what Succinct provides you right now, anyways. But I do think that there are a lot of interesting systems that just use append, just like key value stores and NoSQL stores.
Okay.
Thank you very much.
Thank you.